Well, good evening. I'm Charles Schultz, and this is the randomizer for the 13th of May, 2022. And tonight's term, there we go, there's the title. Tonight's term will be interference. And there are numerous contexts we can take that term in. Some people would think of interference on a radio or video channel or on a signal of some sort. But we also have another term, and that's quantum interference, and we're going to look a little more to that because it has something to do with the stability of all matter. And so this is, it might seem like a tiny term, interference, and yet, believe it or not, it's one of the most important things to us because it keeps matter stable and solid. So we'll have a look at that very briefly here. I'm going to encourage people to go to schultzlaboratories.com or universesciencecenter.com. Join us, become a member, and support the growth of our galleries and our exhibits. If you're an educator, we can set a classroom and a gallery up for you in virtual space where you can display your works and share your teaching, your knowledge with other people all over the world who want to become students. Also, the randomizer is now happening on weeknights of Monday and Friday only at 6 p.m. Eastern Standard Time. We have a robotics classes being carried out on Mondays at 9 p.m. and they're actually pretty exciting, a lot of fun, interesting things, bringing hardware to life and making it do stuff. We get into the hardware, the code, the dynamics, the batteries, all the things that it takes to make a robot work. So let's get right down to the point, and that is interference. So I'll briefly cover the electromagnetic type of interference. A lot of people are familiar with the fact that radio broadcasts often get noise, video broadcasts often get noise, and this is from the old television by antenna days. Interference turns out to be any sort of noise that falls right smack in the middle of your signal and interferes with its ability to be transmitted. And that makes perfect sense. And if you listen to the noise of the cosmic microwave background, you'll find that interference noise actually had a very significant part to play in our understanding of microwave background, the Big Bang theory, and many other things. A couple of radio engineers, Penzias and Wilson, were working on microwave broadcast amplifiers and hardware. And when they put a large horn on their system to check the amplifier, they found that when they aimed at the sky, which should have been silent, they got a persistent low-level white noise. And they were rather stumped by that. So out of curiosity, they wondered if there was something wrong in the circuit, and they blotted out the input channel, the noise went away. Then they threw a cover over the horn, and the noise went away. And that proved that it wasn't in the circuit, it was outside. So after a little bit of research, they discovered that there was a white noise microwave background to the entire sky in all directions, and it was very, very uniform. Well, today we obviously understand what that is. That is the flash and the bang from the creation of the universe, and that noise has spread out as the universe has grown. The wavelengths have stretched and stretched until now it is less than 3 degrees Kelvin energy-wise, temperature-wise, of microwave energy permeating the entire sky almost uniformly. There are minor variations which appear to be quantum noise from the time when the universe was as small as a proton or smaller. So, and there is still considerable debate over that by many people, yet it seems to be one of the foundations. Looking at the sky, we can see that that noise came from some source. And if you calculate backwards, run the film backwards, it indicates at that point, that very tiny universe was exceptionally hot at that time. But let's get to the other form of interference. Now, we have all probably heard of the two-slit experiment, where a couple of laser beams go to two slits in a material, and the laser light shining through makes a pattern of waves that interfere and make stripes. And you'd think, well, how does a light wave make these individual light and dark areas? It's actually very simple. You can imagine when you drop a stone in a puddle and the ripples spread from the stone, that the waves have high and low energies, and they are above and below the actual flat surface, the undisturbed surface level of the water. So a wave has a crest, which is the high point, and a trough, which is the low point. So these waves have a crest and a trough spreading out from a center point. What happens if you drop two rocks close together? The waves merge as they cross each other. And if you know your math, if you add two highs, it makes a higher point, and two lows makes a lower point. So you get higher and lower crests and troughs. But what happens if a plus wave and a minus wave of the same magnitude come together in the same spot? They neutralize each other. They cancel out to zero, and you're at the normal level of the water for that instant. What if you could make standing waves that matched each other in just that manner? Then there would be zones where those waves canceled out, and zones where they added up, and zones where they subtracted. Well, physicists working in microwaves found a way to use this effect to cancel out or add together the waves from various feed horns or sources of microwaves in such a way that they could literally produce a steerable beam by changing the time delays or the phases of each of the wave sources. So if you can imagine 5, 7, 15 microwave horns in parallel, all aimed in the same direction, and then turned on with a constant signal coming out of all of them, and then you vary the phase a little, you can see that the waves will overlap and add up to make something like a beam. And by changing the phases, you can steer the beam in various directions. Well, this is called phased array methods. So when you have a phased array, you have some array or gathering or group of multiple sources or listeners, and you add together the contents of all of those signals being either broadcast or received in such a way to produce a tunable, movable source or ear. So non-moving arrays of phased emitters or receivers can actually steer all around with no visible or actual movement, simply by changing the combination of the wave fronts. But there's more. While this works very nicely with electromagnetic waves of all types, such as microwaves or even laser light, there's another place where it occurs. There was a fellow by the name of de Broglie who figured out that particles can have wave components and waves can have particle components. Now, this is one of the fundamental questions about quantum mechanics. Are things particles or are they waves? Photons obviously show both qualities depending on how they're generated or received, how you try to detect them. And quantum mechanical experiments show that photons can have either of those properties, but they also confirm that matter itself can act as a wave, that it can interfere in such a way that the matter will be here and not there, just like the phased array broadcasts of microwaves. So imagine what that really means. Matter is a wave. Wave-like forms, as a rule, don't tend to have momentum or inertia the way we usually perceive them. But it goes even further. What if you look at electrons themselves, single electrons? Now, they're very tiny particles. There's not a whole lot of matter to them, not much mass at all. And when you look at an electron, it's one of the tiniest fundamental particles, and it certainly is one of the tiniest ones with a charge that is stable. Many people ask the question, if electrons are negatively charged and the nucleus of an atom is positively charged, why don't the electrons simply zip right down and hit the nucleus and neutralize the charge? You would expect that that would be the case, because the closer they get, the stronger the attraction becomes. But there's a reason that electrons do not spiral in and hit the nucleus. Let's imagine, first of all, what it would look like if an electron did that. The electron would be orbiting the positively charged nucleus, and as it got closer and closer, it would be speeding up. The change in velocity of an electron causes it to emit energy. And this giving off of these photons is exactly how gases that are ionized glow at certain colors, like a neon lamp. Well, electrons can also be slammed to a stop by hitting a target, and if they have a lot of energy, they can give off a glow such as X-rays. X-ray guns use a charged metal plate that's positively charged and shoot a beam of electrons that is negatively charged, and they charge that plate to thousands, tens of thousands, or hundreds of thousands of volts. The electrons move forward and accelerate to incredible energies, but when they strike the metal plate, they slam to a stop. What happens to their energy? It is radiated as a photon, X-rays. And this is how X-ray tubes work. A vacuum tube with a cathode beam as it's called, of electrons attracted to a positive metal plate, slamming to a stop and giving off a glow of X-rays. Now we've gotten very good at controlling this, but think about it. If the electron is giving off photons of energy every time it changes velocity, such as making a turn or slamming to a stop, why couldn't it just give off energy, spiral in, and strike that nucleus? The answer is actually very simple. At this scale of matter, the electron acts more like a wave than a particle. And the wave-like aspects of the electron perform interference. This is the sums and differences of those overlapping ripples in the pond. So the electron actually interferes with its own presence in such a way that the minimum energy place for it to be is in a shell, a nearly spherical shell around an atom when it's undisturbed. So if you looked at an atom and you used these special eyes that could see the charges of those particles, you would see the layers like the layers of an onion, different sizes, but they would be the layers that the electrons are trapped in, the orbital shells. And if you know anything of chemistry, you know what orbitals and shells are. SPDF, the lettering for the shells in each of the orbits that the electrons can exist in. So if you look at molecules and you can see them by the charge patterns, the electron patterns around them, you would see amazing fields of repulsion that keep the electrons, that keep matter from squishing into each other. Think of the opposing poles of a magnet, north to north, and how hard you have to push to get them together. Well, because the outsides of atoms are negative, and the outsides of other atoms are negative, as a general rule, they'll reach a point where they repel each other just like those magnets. And this is what makes matter solid. So if the electron could spiral into the nucleus, that solidity would be gone. Again, why doesn't it happen? As a rule, everything goes to the lowest energy state. You can imagine corrugated metal, like you see on rooftops or old farm buildings sometimes. And imagine pouring marbles on that corrugated metal. Now, it would be obviously very noisy, but what would the marbles do? They would all fall into the troughs and the corrugations. None of them would sit on the points up at the peaks. They can't. Because if they start to move, they lose energy, they go downhill, give up their energy, and they stay in the trough. Self-interference of an electron, the electron wave, is what does this. When the waves combine, the lowest possible energy state is to be in that shell around the electron, the atom. And so again, looking at an atom, you will find layers like electron layers, like an onion. And each of those layers is like a single racetrack that electron can very comfortably move around in at any time. And don't be fooled. They don't orbit it like a planet orbiting a star. They orbit it by ping-ponging around at random to the points in space around it, and it looks like it's almost instantaneous. It's a quantum transition. But the electron's probability of being in a certain spot in this process is what creates that shell. So imagine when you look under a microscope slide at little pieces of material in water and how they jiggle around as you're looking, Brownian motion. These little particles are being struck by water molecules from all directions at different speeds, and it's making the particle react every time the water molecules strike it. The noise of the vacuum, quantum noise, makes electrons and other particles do exactly the same thing. This is like the Brownian noise of the foamy structure of space-time. This is known as Wheeler space. 1 times 10 to the minus 33rd centimeters, a tiny little area that's so small that the noise of the vacuum itself is significant. Particles react to the energy appearing and vanishing at this point by jiggling in this Brownian pattern. For electrons, what ends up happening is they jiggle around in this onion layer, in this shell. So they're ping-ponging around like Brownian motion, but they're staying in this spherical shell. If it's undisturbed, it's a sphere nearly, and they do this all the time. And it just happens that if you have two electrons in the shell, they have to swap polarities, so one is spin up and one is spin down. After all, if they were both spin up, they'd be in a high energy state. They're going to fall into a low energy state. When you get all of the electrons in a shell, and the shell is complete, all the electrons are spinning in different directions. In 3 space, that means you got an up-down pair, a right-left pair, and a forward-backward pair. And inside that shell of 6, there's usually a shell of 2 that are up and down, opposite directions. So the SPDF labels you see on the shells of electrons for atoms correspond to these up and down spinning electrons moving in pairs in each of these shells. And the interference wave of the electron creates the shell, and that's why it can't spiral in. It would take more energy to be closer to the nucleus than it would be in that shell. This is why matter doesn't collapse, quantum interference of electron waves. So I hope this has been informative and you've learned something interesting, that matter itself can actually take on a wave-like property. And believe it or not, physicists have succeeded in turning electrons and even whole atoms into wave-like structures that can pass through prisms and diffract and leave wave-like patterns behind. Perhaps with the right transformation to wave structure, we could learn to teleport objects from one place to another, where they go from particle to wave state, travel over here, and reintegrate as a particle again. That would be a real advancement, and it's something that people are working on. So, for now, the floor is open for questions if anyone has one. Meanwhile, I'm going to encourage you to go to schultzlaboratories.com or universesciencecenter.com. Sign up for our classes, join us for the randomizers, and sign up as a member and support the growth and development of the virtual science world that we have inside our virtual space. The Universe Science Center is one of the most unique and interesting learning environments that there is, and we encourage you to explore it and play with it. Become a member, support us, and its growth. And thank you for that. So I don't see any questions on the floor. We're going to move along with my quote for the day, and this is a great one. It says, "Call to me, and I will answer you, and show you great and mighty things which you do not know." And that is Jeremiah 33:3. Well, I hope you have a wonderful evening. It's been a great... Oh, here we go. We have a question. Why do electrons emit X-rays when traveling through magnetic fields? That's an excellent question. All right, so a magnetic field creates a zone known as equipotential. When you have waves of magnetism, or I should say magnetic lines of force, and an electron passes through those lines, it orbits around in the zone where the electron's energy remains uniform. If the magnetic field varies rapidly or greatly over distance, when the electron is passing through the field, the electron has to curve to maintain its energy level. The change in velocity causes the emission of the photons by the electrons. So an electron passing through a magnetic field curves to meet the equipotential, the zone of equal energy. In doing so, it changes velocity. When it changes velocity, it emits photons. And that is your answer. So there are only 5 ways that an electron will emit a photon. And Compton emission is one. Changing velocity is one. And you can look up the 5 different ways. That's a fascinating thing to see, how electrons can emit photons. Moving through an electromagnetic field or a static magnetic field, we get X-rays, and we see them in space when the electrons that are freely moving through space move through the powerful magnetic fields of Jovian planets or neutron stars or even regular stars. And when solar flares occur, the plasma that is emitted is extremely hot and giving off electrons and protons, both of which moving through the magnetic field can give off X-rays. Protons give off very powerful X-rays when they curve because they have over 1,800 times the mass of an electron. Electrons give them off very readily because they turn very easily. So that should, I think that covers the emission of X-rays from electrons moving through a magnetic field. And if there are any other questions, Floor still open? And I don't see any, so I think that might have answered it. And we're going to have a wonderful evening. I hope everybody had a great Friday the 13th today. Enjoy your life, and as I always say, make the world a better place. And we'll see you on the next randomizer. I'm Charles Schultz. Thank you for attending.